day and welcome back to the course. From the previous class, we discussed the fundamentals of time analysis, time efficiency analysis, where we talked about the discovering the running time of an algorithm using the basic operations. And we already in the previous class we talked about the basic operations execution time and the count of the basic operation. And then in this class, we are now going to be talking more about the order of growth and the asymptotic analysis, right? So now, from the previous class, we had C of n. That was where it became the basis for us actually to give some reasonable estimates of how fast or how slow our algorithm will be when the input is being changed. And I must have mentioned in one of the classes that the algorithms would either be slower or be faster depending on what input is being put into it. So if you put small input, the algorithm will be naturally fast, but if you put a large input, that's when we know if our algorithm is doing better or not. So we are focusing on what? We are focusing on the count order of growth. And the order of growth is stemming from, what happened when you put something inside the input. When you put an input inside the algorithm. So let's say we put 5 into the algorithm and then it took us 5 minutes to come out. We can say, 1 minute for one input, right? What happens when we put 20? Will it be 20 minutes that it will take the algorithm? What happens when you put 20 and then the amount of time it takes is not 20 minutes but 200 minutes? What function is that? What happens when we put 200 and then it skyrockets to taking about 75 days before it can yield the result? When you put five inputs or five whatever, and then you're getting 5 minutes, see that order of growth is weird, but it can be defined. And then we can have the order of growth being polynomial, like n square, n cube, n raised to power n, depending on how crazy the stuff is. But that you just get the picture that we are dealing with the order of growth, how fast the algorithm can, how the problem can grow, or rather based on the input size. And then we know that for small input sizes, they don't really help very much. So we are saying small inputs are bad for judging algorithms. You can think you've made the best algorithm in the world when you are running it with 5, 10, 15. When they put 2000 and then the algorithm crashes your computer, then there's a problem. So for all large values of n, the function's order of growth is what matters. So excuse me. So now we have a table, right? And this table goes from n all the way to n factorial, right? So look at this. We have the inputs being n. So we have 10, we have 10 square, which is 100, and we have 1000. In a logarithmic function, what do you have? You have for every 10 elements, you are going to have 3.3, and then for 100 you have 6.6. You see that order of growth, how fast is it growing as a result of the big input sizes? It's not growing by much, and this is a very, 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 very efficient stuff, a very, very efficient algorithm if it's using logarithmic time, but it's not very common and it doesn't happen often. So for 3, 6.6, and 10 for 1000, which is crazy if you ask me. Now linear functions are the ones that, okay, we know that we put 5 people inside this list, it takes 5 minutes to process it. We put 10 people inside the list, it takes 10 minutes to process it. We put 100 people into the list, it takes 100 minutes to process it. We put 1000 people in the list, it takes 1000 minutes to process it. But then if you look at n log n, which is linearithmic functions, it says 3.3 times 10, which means it's both having the logarithmic function and linear function. And then we have all that. Then from the polynomials is where we start to see some real order of growth stuff going on. Now we put in 10 and then we have 100 as the order of growth. Like it just, because of the input size, it expanded, it grew. So the effect of the input on the algorithm is what we are recording as the order of growth. So the effect of the input is causing the algorithms to react like this. So we put in 100, we are having 1000, Is this 10,000? This is 10,000 actually. And then we put in 1,000 and we're having, I think, maybe 10 million. So for n cube, it's even worse. But 2 raised to power n, it's just crazy. You put in 10 and you're having 1,000. You put in 100, you're having something. I think this was 30. I'm not sure, but it was a gigantic amount. And then for n factorial, let's not even talk about that. Factorial functions are crazy. All right, so we noticed from the table that log n was the slowest growing function, and that's what we want. We want a function that grows slowly. We don't want some massive spike in problems because of the input size. We don't want the input size to just suddenly cause a massive growth. We want small. Small is good. We don't want complex. We don't need complex here. We want simple. Simple is good. So 2 to the power of n and n factorial, their input size, their order of growth is just crazy. Um, all right, so then it brings us to asymptotic analysis. So what is asymptotic analysis working on? The main idea behind it is to measure the algorithm's efficiency without any machine specific constraints or constants. So we are just basically trying to know how efficient an algorithm is, but we don't want the stress of having machine constants involved. We don't want to have to implement the algorithm. We don't have to look for we don't have to create the program and then be checking for time comparison. It's good for measuring the efficiency of an algorithm without any of these hassles, and then we use it to compare and rank the order of growth. That's what we do with that. um, Now, asymptotic notations, what are they? They are mathematical tools for representing time complexities of algorithms. So think about them like sets. So the way we create some form of nicknames is like creating nicknames, or rather, let me just use the example of a crate of egg. So this is a crate of pigeon eggs. This is a crate of ostrich eggs. This is a crate of chicken eggs. So what do they contain? How do they work? We'll look into that. So big. This is the O notation, right? And it's talking about the big O. So what is the big O notation? Big O of g of n, where g of n is a function. Big O of g of n is a class of functions t of n. That means there's a set of functions that we are dealing with. We're not just talking about one thing. We're talking about a set of functions. Now, a set of functions that grow no faster than g of n. That means it's limited by g of n. It can't get bigger than g of n. It can be either as big as g of n or lesser than g of n. That's what the big O is just classifying. So we can have anything inside anything. We can have, let's say, n cube, for instance. If g of n is n cube, we are saying that if something is going to be in the big O of n cube, it's going to have to be either n cube or less than n cube. So it can be n squared, it can be n. All of these are permitted, but it cannot be n raised to power 4. This is not going to fit into the G of O. It's like putting ostrich egg inside a chicken crate, chicken egg crate. It's not going to work. You need maybe a big egg at most, or a smaller egg, or the smallest eggs possible. You can even fit in a pigeon's egg into a chicken egg crate, but you can't fit an ostrich egg into a chicken egg crate. It's not going to work. So we have the class of functions t of n that grow no faster than g of n, and then we have a graph to show this. You will notice that there is a slight blank. This doesn't matter. So this is basically dealing with where the input size is small. Let's say we have 5 to 10 to 15 to 20. It's not so important that we really need to measure, because come on, everybody's baby is fine until when they start breaking chairs and tables. Forgive me for saying that. So when it's the input size is small, nobody really cares. You can't exactly define how good the algorithm is based on that. You saw how the logarithmic functions work. 10 gave 3.3. It didn't look like a big deal. 100 gave 6.6. That was looking like a little bit of a big deal. But then 1,000 gave 10. That's crazy. Comparing that with the factorial, put 1,000 factorial. That's infinity in a way. I don't think we have a number for it. So it's just showing how important it is for the size. Now, we realize that it is bounded above. We see that this guy is bigger than this guy. So the rate at which this guy is growing does not match with the CG of n, where C is a constant multiple. It can be any constant. We've not specified what the constant is, but it's just for you to know that these functions T of n do not grow faster than G of n. They can be equal to G of n in terms of growth, order of growth, but they cannot be faster than it. They can be lesser or equal to. So what is the mathematical definition of all of this? T of n is a member of big O of G of n if T of n is bounded above by a constant multiple of G of n. And that's what this is. This is a constant multiple. We did not say what the constant multiple is, but we say that there is a constant multiple of G of n for all large n. We are not dealing with small values here. We're dealing with big values. One big. We are dealing with big values because that's how we really know the weak points. That's when the furor of the chicken, as Yoruba will say it, will be revealed to the public. So, and how is this well, the order of growth of T of n is less than the order of growth of G of n. I've mentioned that, where C is the positive constant and n naught is the non-negative integer. That's for the small values, right? And then this is the mathematical formula. We've known that already. The T of n is less than or equal to the CG of n, where the C is the constant multiple, and then G of n is the function that we are trying to use as a pattern matcher. And then there's the for all n greater than n n naught, n greater than or equal to n naught. This is just trying to say, okay, now for big values, and talking about large values n. So given an example, let's say 10n square is an element of the big O of n square. Is this true or not? Since we have C of G of n, which means that there exists at least a function that is bigger than this 10n square inside this big O. This C of n can be 55, it can be 80, and 80n square is greater naturally than 10n square. But since we have so many possibilities that can be here, then this 10n square is an element of the big O of n square here. Moving forward to the big theta. This is big theta. Oh. So for the big theta, we are dealing with the class of functions T of n that grow at the same rate as G of n. So it's not a matter of which one is growing faster than which. There's no less than, there's no greater than there. It's exactly the same rate of growth as G of n. And if you look at this graph, we've already mentioned how this part is not important. Now it's bounded above. There's G of n is bigger and G of n is smaller, and then it's right in the middle. I'm just trying to say that it's not greater than or lesser than. It is directly equal to. It's equal to. It cannot be bigger or smaller than G of n. That's what this bounded by is saying. So the mathematical terms for all of this is T of n is a member of big theta of G of n if T of n is bounded above and below by a positive constant multiple of G of n for all large n. And then this is the formula. We have it bounded above, it's bounded below here and bounded above for all large n. And then we just have to differentiate between the n naught here and the n itself. Having said that, then moving on to big omega. Big omega, by the name big omega, suddenly it sounds more like a boss name. What this is just dealing with is a class of functions T of n. So T of n is a class of functions. It's not just one function. It's not just but then we can give examples, but usually it is can give examples like, let's say this guy, but it's a class of functions, so it can be anything as long as it fits into that. And what is the condition for fitting? Grows at least as fast as G of n. So this one is dealing with greater than or equal to. So if the function grows faster than G of n, that's fine. If it is growing at the same rate as G of n, that's also fine. And if you look at the graph, you see that the T of n is skyrocketing way beyond G of n. So how do you explain this in mathematical terms? T of n is an element of the big omega of G of n if T of n is bounded below. The bounded below means that it can't go below G of n. It can go above G of n. And then you can see that we are using this to more of group functions. It's not dealing with one particular function or anything. It's just like basically creating a family for a value. It's like trying to, it's not exactly comparing two distinct algorithms. It's rather trying to just fix an algorithm into a family of algorithms. So it takes this entire this guy and puts it into a family. So this is the stuff bounded by some constant multiple of g of n, where n is a large value. And then we say n cube is a member of big omega of n square, and that is true because it can grow much faster than n square, and that fits into this. So looking up at, we have this now explains what we are trying to do very well. So we have the set is more like, I think this is a Venn diagram, right? So the Venn diagram has an intersecting point and it has a upper point and a lower point. So for the upper point, this guy is talking about the big alpha, where this is bounded above, where this guy is, sorry, is bounded, g is t of n is bounded below by g of n. As you can see, it's bounded below by g of n, so it can only go up. Well, this guy is bounded above and below by different values, but it's equal to g of n. This one is bounded above by g of n, so it cannot get bigger than g of n. This is a very, very good diagram for explaining all the same things. So for big O, it grows no faster. For big theta, grows at the same rate. For big omega, it grows at least as fast as g of n. So now we've talked about asymptotic notations and everything, but there are better ways for comparing two actual order of growths, right? We use limits, and then for limits, they are we are dealing with a ratio here. We are dealing with a ratio, and since we are dealing with a ratio, we have two guys. Let's say we have 10 square and 10 cube. Knowing that, um, comparing them will give three possible results. It can give 0. What does 0 mean? 0 means that the t of n is less than. So if the result of this operation is 0, then it says that the t of n is less than the order of growth of t of n, rather, is less than the order of growth of g of n. The order of growth of t of n is less than the order of growth of g of n. What if we have a constant that is greater than 0? It can be 0.5, 0.2, anything that is just greater than 0. Then we can see that the t of n is in the same, it grows at the same rate that g of n is growing. And then if we have it to be infinity, then we are saying that, okay, like we've done all of what we should do, and then it's yielding infinity. We can say t of n is greater than, like, the order of growth of t of n is greater than the order of growth of g of n. So using connecting that to their asymptotic terms, you can see that since the order of growth of t of n is less than the order of growth of g of n, it's more likely to be in the big O of g of n. Now, when the t of n, the order of growth of t of n is the same as the order of growth of g of n, then we can see it's in the big theta of g of n. When the t of n, the order of growth of t of n is greater than the order of growth of g of n, it should be in the big omega of g of n. So now using I didn't mention. Now, in the case where we are having to use the we are doing a ratio, you can have stuff like this going on indeterminate. Limits don't like these guys. We don't want indeterminate. We want either it should be 0, or if it's infinity, it should just be infinity in peace. But we do not want since infinity is actually a value that is allowed, but indeterminate is not a value that we want. Indeterminate is a mathematical improbability, and we do not want that. So what do we do when the f of n is equal to g of n and is equal to infinity, and we are doing a thing of ratio of the two of them? We'll be having indeterminate, and we don't want that. So we can pull off the L'Hopital rule that says what? We do the derivative of the f of n, and we do the derivative of the g of n individually. But then since it's still a ratio, we'll do that. And then we should then have a better chance of knowing whether it should still be indeterminate or not. And if it's going to be indeterminate again, we should do this again until we don't have indeterminate values. As long as we keep on having infinity over infinity as values, we are not able to work with the limit. So we have to get into a situation where it's either 0 or a constant or infinity. So using an example, let's say that we were given these guys, and we know that since since 10n square is being put together with this guy, we can say that 10n square is actually a member of the big O of n cube. But then let's use the limits to deal with that. So we have lim from n tends to infinity 10 square divided by 10 cube, or n cube rather. So let's put in the value of infinity first. We have 10n square. So 10 the bracket infinity square divided by infinity cube. This is going to be indeterminate, and we do not want this. So what do? We do the derivative of this. So f prime of n for this guy is going to be 20n, and then the g prime of n is going to be 3n squared, right? So if we put that in, we have 20n divided by 3n, sorry, yes, 3n cubed. Putting the infinity again, we have 20 infinity divided by 3 infinity square, which is indeterminate. And since this is it, we can still work with this. So let's go further again. At this point, we'll have 20, because that's what the derivative will give. And g prime of n will be 6n. What would that look like? We have 20 divided by 6n. Now, if we were to put the values, we have 20 divided by 6 in the bracket infinity to be 20 divided by infinity. This should give us 0, but let's just say we want to do it. We don't like what this value is giving us, 20 divided by infinity. We don't like this guy. So let's go one more time. When we do the g prime 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 of n, would have 0. And then when we do the g prime prime, sorry, g prime 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 of, oh yeah, f prime 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 rather. F prime 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 of n is going to be 0, and g prime 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 of n is going to be 6. So 0 divided by 6 is 0, and if you remember the previous thing we talked about, 0 says what? 0 says that it is the t of n is less than g of n, and then what is the order of growth rather of t of n is less than the order of growth of g of n, and then that should be in the big O notation. And that's exactly what we've just used the limits to do. So thank you for watching. I'll see you in another video.